For those who work with or around radiation, one of the most important factors is an awareness of the levels of radiation around them. A basic understanding of the different types of detectors and how they work may help us find the best detector for the required task. As mentioned in part 1 of our module, radiation detectors are generally classified as counters or severometers, dosimeters or dosimeters, and spectrometers. In this part 2 of our module on radiation detection, we will discuss the operating principle of gas-field detectors and how they can be used for all those above mentioned detector classifications. I'm Cherry Ann and I will be your facilitator for this module. The most commonly used detector, because of its ease of use and ruggedness, is the gas-field detectors. They are easy to construct and operate and can detect all types of radiation particles. However, the density of the stopping material is low because it's a gas. There are several types of gas-field detectors. We have the ionization chambers, proportional counters, Geiger-Müller tubes. And while they have various differences in how they work, they are all based on similar principle. So when the gas in the detector comes in contact with radiation, it reacts with the gas becoming ionized, and the resulting electronic charge or collection of charges are collected and measured by a meter. So here we have a diagram of your gas field detector. This type of detectors are usually cylindrical with two electrodes. One in the middle, the anode, where the electrons are collected, and the cathode on the wall of the cylinder, which attracts the positive ions. This type of detector rely on the ionization of the filling gas. The ionization energy, or the energy needed to create electron ion pairs, is about 35 electron volts per electron pair. When a high voltage is placed between the two areas of the gas filled space, the positive ions attracts to the negative side of the detector, which is on the wall, and the free electrons will travel to the positive side. Then the charge builds up, causing a voltage change in the circuit, and can be measured by this electrical current measuring device, sometimes referred to as the pulse. The major differentiating factor between the three types of gas field detector is the applied voltage across the detector. It determines the type of response that the detector will register from an ionizing event. So this figure shows the relationship between the high voltage supply and the charge collected or pulse height. So as the voltage is increased, charge collected increases and with a certain relationship. It is also important to note here that this type of detector can discriminate radiation sources, but up to some applied voltage region. So the low penetrating alpha and beta particles can enter the gas chamber via an end window, while the high penetrating gamma can enter via the outer wall, or neutrons also can penetrate the outer wall. So let us look closer what happens to each region with increasing applied voltage. So in here, we have the recombination region, wherein with no or very little or very low voltage, the electron ion pairs will simply recombine. Some will be collected and also register a pulse. That's why we have here an increase in the pulse height. But when the voltage is high enough to stop recombination, the detector now is in the ion chamber region. So in here, we have complete primary charge collection from the direct ionization. The lines here represent the amount of charges from gamma, beta, and alpha particles incident on our detector. So at this voltage, the detector only registers pulses from the primary ionization that is caused by the interaction of the incident particle in the gas chamber. So these are the ionization produced. So thus, the measurement the detector records is directly proportional to the energy absorbed by the detector or the charges deposited in our detector. For this case, this is particularly useful to measure absorbed dose over time and used in accurate dose rate measurements. So this is our ionization chamber example, where in A, this is the wall which serves as the cathode, and B, the actual anode or the positive electrode. We have the beta window made of thin foil, which will trap which won't allow the alpha and beta particles to be detected. So this is made up of toughened plastic or aluminum. So the direct current amplifier in our detector measures only the low current produced by the primary charge, which is proportional to the intensity of radiation. So the ionization current indicates the exposure rate or the amount of charges that were produced. So this type of ionization chamber measures low and high energy photons, alpha and beta radiation, and must have thin walls or windows for beta and alpha detection. Ionization chambers have good stability because of simple mechanism and chamber structure and can be used for a relatively high dose rate because of its low sensitivity. These are the examples of ionization chambers that we use in the field. These are for those dosimeters, survey meters, and for radiation detection measurements. So the next step on the voltage scale for a gas field detector is the proportional region. So at sufficiently high voltage, charge multiplication may occur. They perform proportional counters perform similarly to an ion chamber in that the interactions with radiation create ion pairs. However, they have strong enough voltage that as the ion drift towards the detector anode, the voltage increases until they reach a point where a gas amplification event occurs. So accelerated electrons gain high energies to cause further ionization as seen in this figure. So gas amplification means that the original ions created by the reaction causes further ionization reaction, which multiplies the number of electrons and thus multiply the strength of the output pulse measured across the detector. But still, the resulting pulse is proportional to the number of original ion pairs that was formed. The energy of the radioactive field is thus proportional to the number of charges generated in our detector. So here, the charge multiplication occurs, and over a range of applied voltage, the detector output pulse is still proportional to the amount of energy deposited by the radiation. And since they produce more electrons than primary ionization, these proportional counters are more sensitive than ion chambers and can be used for low intensity field radiation. Likewise, they are able to identify any type of particle and its energy. Proportional counters are specially used for contamination meters and are capable of measuring low dose rates. They are also accurately useful for spectrometry, for neutron detection, for discriminating between ionizing particles, and absolute measurements of activity of beta emitters. The usual gas in our proportional counters are P10 gas, a mix of 90% argon and 10% methane, and noble gases such as argon and xenon. But for proportional counters used for neutron detection, field gas must be um, materials or nuclides that have high absorption cross-section to thermal neutrons. So this is an example of a xenon proportional counter. This is a BF3 neutron detector, and this is another helium-3 neutron detectors. When the neutron detectors are placed inside this Bohner sphere, they can be able to detect higher energy neutrons. And it's very important here that a stable voltage supply is used to ensure that any change in output is related to the change in incoming radiation rather than a change in the applied voltage, since we know that the input energy is proportional to the charge output of our detector. So since also this type of detectors react differently to different energies, they are able to tell which um, source of radiation they come in contact with. And with a proper pulse-side discrimination circuit, they be able to distinguish between the types of ionizing radiation on the basis of their ionizing ability or the number of charges that are produced. At higher voltage, shown in region 3, we have accelerated electrons gain high energy to cause further ionization. And amplification happens, but only to a limited proportionality range. So in here, the pulse height no longer correspond to the primary ionization. And we call this region the limited proportional region. The major or the last class of gas field detector is the Geiger-Müller tube, the origin of the name Geiger counter. Operating at much higher voltage than other detector types, they differ from other detector types in that each ionization reaction, regardless of whether it is a single particle or a strong field, causes gas amplification across the entire length of the anode tube. So the increase in voltage causes an avalanche of ionization coming only from a single ion. The UV rays also from the excited atoms and causes Townsend avalanche producing electron hole pairs further again and again. So thus they really only function as simple counting devices used to measure count rates, or with the correct algorithms, maybe they can also be applied for measuring the dose. But here, secondary ionization begins to swamp the original primary ionization signal, and thus all the information from the primary ionization is lost. So the charge collected is no longer proportional to the primary ionization. We have no more information about the source of this ionizing radiation. And after each pulse, the Geiger-Müller counter has to be reset to its original state because of the Townsend avalanche that is happening. This is accomplished by quenching or using an inert gas or traces of organic and halogen gas called quenching agents. The quenching can be accomplished electronically by temporarily lowering the anode voltage on the detector, which allows ions to recombine, but it can also be accomplished chemically using these quenching agents, which absorbs the additional electrons to allow it to collect further ionization. And due to the extensive reaction in Geiger-Müller tubes, they experience high dead time rates, meaning that there is a lag between pulse cascade, and when the gas is able to revert to its original state, they can already again be ready to detect another pulse. So these are examples of Geiger-Müller detectors. This is very high sensitivity detectors and is mostly used in low intensity fields. And it only requires a moderate stable voltage, a simple amplifier, and other inexpensive components, including a rate meter, to construct a useful instrument. As I've said, the output is always the same magnitude. So basically, these detectors can be used to determine the presence or absence of radiation and can detect alpha and beta photon radiation. So at higher energies, we have what we call the burnier anode region, or the continuous discharge region, where further increasing your voltage can cause your anodes to burn. Okay, so question number 5. Which of the following statements about ionization chamber, a type of gas field detector, is false? Question number 6. Proportional counters are gas field detectors that operate at higher voltage. Due to this, gas amplification occurs, and the amplification is linearly proportional to the increase in voltage. True or false? They are useful for some spectroscopy applications since they react differently to different energies and thus are able to tell the difference between different types of radiation. And then for Geiger-Müller counters, question number 7. GM counters are very sensitive to radiation and is mostly used for counting and detecting presence of radiation in field. So select the applications of GM tubes from the following choices. Write your answers on the given space on your Canvas account. So in summary, our gas field detectors are made of 3 types depending on the applied voltage. You have the ionization chambers that are able to detect alpha, beta, gamma, and primarily used for dose and dose rate measurements. Then we have proportional counters that can determine or can detect X-rays, beta, gamma, and neutrons, and primarily used for spectrometry and also be for dose rate measurements and contamination measurements since they are sensitive to low intensity fields. And for Geiger-Müller counters, they can detect alpha, beta, gamma, X-rays, and sometimes neutrons, and appropriate for dose and dose rate measurements given the proper algorithm and contamination measurements because of its high sensitivity. So the special features, ionization chambers used in accurate dose measurements. Proportional counters are better response to low energy photons, low dose rates but with high technical requirements. And the Geiger-Müller counters are relatively ruggedized and operates in simple output circuits and appropriate for contamination measurements. So that's it for gas field detectors. Next up is solid state detectors.